Alright, welcome to the optional session. In the optional session we will define entropy, cross-entropy, as well as KL divergence. KL divergence allows you to compare two distributions. Yeah? Cross-entropy is actually the same. Cross-entropy will be the cost function that we will use when we deal with classification problems in deep learning, neural networks. But before we get into all these details, let's see where we came from and where we are. Yeah. So we basically focused on supervised learning. That means that the training data you get is labeled. Yeah. And in supervised learning, you have regression classification. Regression problem, remember the housing price prediction case. We defined a cost function, that is the mean squared error, and that was the formula. So you take the square of the difference between the real y and the y predict. Yeah? Then you sum it all up and divide by m, and m is the number of samples. Now in classification, what cost function should we use? It's not that obvious. So how do we define a classification problem in general? Well, you have data. You have a data set D. And the data set D is drawn from a distribution P. And the distribution P is unknown to us. We don't know what this distribution is. It's a probability of seeing the label y given x. The whole essence of machine learning is to come up with this distribution. And we've seen several examples, like in naive Bayes, we have a specific way to get to this distribution using Bayes' rule. And we also said that the mean squared error cannot be used for classification problems. Remember, for logistics regression, our cost function was minus the log of the likelihood. So here now we're going to try to have a cost function for classification problems in general. Okay, let's have an example first. Yeah. So we have an example. We have a random variable x, and x can take on a, b, c, and d. A, b, c, and d are animals, and c is a cat, and d is a dog. Don't worry about a and b. Yeah. Before we start training, we have a list of training samples. And I took one training sample, which is a picture of a dog, and this is the distribution. It's clear, A0, B0, C0, D1. D1 is a dog. And we call this distribution P. Okay? Then we train the system, and we come up with a model. Yeah? So after training you have a model, the model or hypothesis H. And you see the distribution is a bit different. Yeah? So we have 0.2 here, 0.1, 0.1, 0.6. It's different, but it's still pretty good. Because if you take the highest probability here, it says it will be a dog. Okay? So the whole essence of finding a cost function, or the whole essence here, is to find out how close Q is to P. Yeah? So how close is the distribution of my model to the real distribution? In order to get there, we need to define something. And let's define information content as IC. Yeah? How do you intuitively understand this? Well, basically, if you're getting information or extra data and you don't know anything more with that data, meaning you've not been added information, then your information content is 0. An example, here the case, we give you a picture of the dog. It's a dog. You know it's a dog. So the chance that X is a dog is 1. It doesn't give you information, because you knew the picture was a dog. So you can intuitively see that the information content of X is a dog is inversely proportional to the probability that X is a dog. The higher your probability, the lower your content. So that means that the information that X is a dog, that X is a dog, is a function of the probability that X is a dog. Yeah. Okay, now let's take a scenario where we have two random variables. We have X, again our animals, A, B, C, D, and we have Y. And Y gives you the information that that animal is available in Singapore or not, lives in Singapore or not. Yeah? So one is that we can see these animals in Singapore. A 0 means we cannot. Yeah? So in this case, the information content of X and Y is the same as the information content of X plus the information content of Y. This is if the random variables are independent. Now we know that here the information content of Y is a function of the probability that Y equals 1. Yeah? And here is the function of the probability that X equals D, for example. Yeah? So basically this means that we have a function here. Yeah, we're going to transform this, and in probabilities means times if the events are independent. Yeah? So it's the function of the probability that X is a dog and the probability that Y is 1, yeah, equals, and then we use these two, probability that X, sorry, it needs to be a function of the probability that X is a dog plus the function of the probability that Y equals 1. Yeah? So go from here to there. I just used functions. And what we see here is very interesting. You go from a product to a sum. And which mathematical operator allows you to do that? Well, it's the log. Yeah? Because the log of AB is log A plus log B. So now we have a formula, right, that the information content of a distribution P equals here. Now let's go back here. Equals 1 divided by the function that, sorry, that's not correct. Equals 1 divided by a function that's the probability that X is D. Okay, this is this one. But I put a function here. So that means that the information content of a probability distribution P equals minus the log of that distribution. So I replaced F by the log, yeah, and I swapped numerator and denominator. So this is basically our formula for information content.